Welcome to NPTEL course on Fractals and Multifractals. So, in this week we are discussing the multifractals and its property. So, in this lecture we are going to discuss the multifractality of the Koch curve and Sierpinski curve through the introducing the probability on it. So, I am just recalling so the multifractal measures. So, here the Holder exponent alpha is defined as ln of mu of box by ln of delta. This alpha is defined as we need to cover the set by the number of boxes of size delta, those boxes having the alpha exponent that we are calling as the n delta. Then L delta follow this power law property, then thereby one can find the f of alpha. Then f of alpha can be interpreted as the fractal dimension of the subset of boxes size delta having the Holder exponent alpha as limit n tends to delta tends to 0. As delta tends to 0, there is an increasing multitude of subset, each characterized by its own alpha and a corresponding fractal dimension f of alpha. This is the several reason for the term multifractals. Now, let us discuss, already we discussed the multifractality of the deterministic fractal Cantor set, then we introduced the probability on it, then we discussed the multifractality, and using the cut copy method, cut and paste method, then we studied the multifractal method. Now, we are going to discuss the multifractality of one Koch curve by introducing the probability on each segments. Now, consider the Koch curve. So, as we know it, after the first iteration we have the line segment like this one, that means the 4 line segments, each of its length is 1 by 3, each of its length is 1 by 3. Now, we are assigning the probability as like this one, probability for the segment we are assuming as P1, P2, P3, P4. For each segment we are assigning the probability such that the sum of the probability equals 1. So, as after the nth iteration we have 4 power number of 4 power n number of line segment, each of its size is 1 by 3 power n. So, now here we are assigning the probability P1, P2, P3, P4, then in a nth step we have the combination of this probability. So, now the measure of this each segment can be obtained as mu I1, I2, In equal to P I1, I2, In, the probability in the combination of P1 to P4. Now, we need to define the partition function. ZQ of delta of the function is defined as summation of mu I power q. I varies from 1 to its size n, the number of boxes. So, we have the 4 power n number of boxes of each of size 1 by 3 power n. Now, this is not MQ, this ZQ. So, at level n, the binomial coefficients then will give the P1 power q, P2 power q plus P3 power q plus P4 power q power n equal to 1. The sum of all the probability will be equal to 1, and I am writing here MQ, but usually we will use the M for the measure of the multifractal measure, but we have to use the Q. The partition functions follows the power law with respect to the tau q, the mass exponent. Now, this one, the number of entered is 4 power n, the 4 power n. The number of interval n of delta which equals the delta power minus d here, which is 1. So, it will form 1 by 3 power df. So, the df we need to write. So, here 4 power n is directional proportional to 3 power minus nd, that is n df. So here by using this relation, the number of box size is directional proportional to the delta power tau q. Then one can obtain tau q as here z here 4 power n directional proportional to 1 by 3 power n. So 3 power minus n. So 3 power minus tau q. So tau q may be this one, the 4 power n number of interval. So this we can write this as here the as a probability we need to multiply by here. So one can obtain the tau q by this relation. So tau q we are getting as this one minus ln p1 power q plus p2 power q plus p3 and p4 power q by ln 3. Then here by taking the Legendre transform, then we need to apply alpha q as alpha q equal to minus d by dq of tau q, minus d by dq of tau q. Then taking we can get the alpha q sum of pi power q ln pi by sum of pi power q. So different value of q gives different value of alpha, because the probability we are not equal, the sum of this probability is equal. So from here then using the Legendre transform, here q f of alpha can be written as q of alpha plus tau q. Then one can get from tau q, here also it is plus, here it is minus, while taking this one it will come plus, and here it is the plus, there is a minor typos. Now f of alpha can be written as q of alpha plus ln of this quantity over ln 3. Here you can observe for different value of q, this alpha q is the different alpha we will get, will the different alphas are associated with the f of alpha q, this f of alpha also the different curve. If you we have to plot this one alpha of q versus f of alpha q, then we will get the multifractal spectrum for the different value of p's as well as the alpha q. Now suppose in the particular case, if you are taking all the probabilities are equal probability in the all the line segment, if you giving the equal probability, then this time p1 power q plus p2 power q plus p3 power q plus p4 power q in all 1 by 4 power q times 4, and this can be written as 4 power 1 minus q. This we will get. Now from here the tau q one can get as that f of alpha can be obtained as q alpha plus ln 4 power 1 minus q over ln 3. So q alpha plus 1 minus q time ln 4 by ln 3. So here the tau q, then f of alpha is ln 4 by ln 3, because we are getting the alpha q as the derivative of minus this one. If you are taking the derivative of this one, then this is our tau q. So 1 minus q ln 4 by ln 3. If you are taking the derivative, then d by dq of tau q, then we will get minus ln 4 by ln 3, then alpha q is minus d tau q by dq. Then one can get from here that alpha q is ln 4 by ln 3. Therefore the corresponding f of alpha is a single value. That means throughout the all the parts, that means we have p1, p2, p3, p4 all are 1 by 4. Then we will get 4 power n number of interval, each of its size is 3 power minus n. That means all the part of the set have the same scaling exponent alpha, that all the line segment have the same scaling exponent alpha, this alpha. Therefore here f of alpha also we can get ln 4 by ln 3, there is no change in the f of alpha. Therefore, this curve becomes the monofractal when you are taking the probability as one, all are equal. If it is not equal, if you are giving the different values, then the q will change. With respect to the q, then different alpha q will get, then we will get the spectrum. That will show it here. See here, the closed interval 0, 1, the unit line segment, we are separating as 3 equal parts, then make it the side of the triangle, then the second iteration also you can apply the same thing. So here the iteration 1, this is the 0th iteration, there are one interval of length 1, the full of red, and here iteration 1 we are dividing 3 equal part, make it this is after iteration 2, because here this is the first iteration, this is 2 and this is 3 and so on, it's going on. Fine. In the 2, here giving the probability value as the P1 we are assigning as 0.4, P2 we are assigning 0.3, P3 is 0.2 and P4 as 0.1. So left to right we are giving the weights as 0.4, 0.3, 0.2, 0.1, the decreasing size, so that the sum becomes 1, the sum of Pi becomes 1. So here to here we are giving the probability like this one. So here it is 0.4 and here it is 0.3, here it is 0.2, here it is 0.1. Now after the first iteration, this one will divide 3 part, this will again 4 equal parts, then there are 4 line segment we will get. So each segment again you can apply this probability, then after the nth iteration we will get so here 4 curve, no, this is in the iteration 2. So in the iteration q we will get 4 power 2 line segment of length 1 by 3 power 2, not 4, and if n equal to 2 this will apply, this is for n equal to 1 and this is for n equal to 3. So the color combination, if all are equal, this is the probability distribution, and 0.1, 0.3, 0.2, 0.1 the color combination is here. So now this color is like the distributed over this region like this one, the probability is given here. Now for finding the multifractal spectrum, first we need to find what is the mu I. First we need to find the mu I. The partition function z of delta is defined as mu I power q. The mu I we are taking as the probability, the combination of these probabilities, so that the mu I power q we will get always as 1, this sum we can get as 1, and at level n all 4 power n segments are generated by the multiplying the weights along the sequence, then zq is the sum of this one power n. I am using zq is the function. So there are 3 power minus n is the delta value. So the zq is directional proportional to the delta power tau q, therefore we can get tau q as like this one. Then the alpha q we can find from the derivative of tau q, one can get this as our alpha q, and here also plus, here also plus, here also it is plus. Then alpha q, from taking the derivative we can get the Holder exponent like this one, the pointwise derivative, then one can get this one. Now for alpha q is once we obtain, it is one can understand from the different pi, p1, p2, p3, p4, different p4 with respect to the q we will get the different values. So this will we get as the in the interval alpha min to alpha maximum, in the interval we can plot this f of alpha curve with satisfying this one can get the curve like this one, the red, that yellow, and this is full of green, and here the purple, whereas these are the combinations, because in each interval it has the red, green, blue, yellow as well as their combinations. So whenever the alpha is small, the large weight more concentration. As we know that whenever the density get increased, whenever the alpha is go to smaller value, that means that red will come here. If alpha goes to infinity, that means the alpha goes to larger value, then small get more spread out. So the small weight is here 0.1, there is a less density here, so that we will get the spectrum like this one. Then we can calculate the width by this probability. Here the spectrum is for the P1, P2, P3, P4, we are taking like this 4 different probability. Now instead of all 4 different probability, you can take all are equal probability, then one can get that alpha is ln 4 by ln 3, it is a constant value, therefore f of alpha is a single point. So by taking the all the probability as equal to 1 by 4, that means as we discussed in the Cantor set, the density instead of probability, if you are taking the density are equal, then f of alpha becomes the constant. It is a single fractal, it is not a multifractal, it will become the monofractal. So you can check here when f of alpha gives the maximum when alpha not equal to alpha naught, it will get the maximum value. This will give the support of the fractal dimension, that is ln 4 by ln 3. This value we will get as ln 4 by ln 3, the support of D ln 4 by ln 3. So here we are explaining the nature of multifractality in the set von Koch curve by introducing the probability, whereas if you are taking the equal probability, then the distribution of these colors are equal here in all the segments, it will equally distribute, there is no non-homogeneous distributions. So if you are taking the different values, then only the distribution of color will be the non-homogeneous, therefore we will get the spectrum, otherwise we will get a single point. Now we will implement the same with the Sierpinski carpet. So consider the Sierpinski carpet. The Sierpinski carpet is, that means we are taking the unit box of each side length is unit, this box we can consider. This box will be divided into 6 squares, 9 subsquares 3 by 3, and the central square is removed. We need to remove this one. Now after the first step, we have the 8 square, each of its side length is 1 by 3. Each of its side length is 1 by 3. So total length 1, so side length we will get 1 by 3 each of it side length. Now for this each boxes, we are giving the probability P1, P2 up to P8 such that the probability, the sum of the probability equal to 1. So the similar like the von Koch curve, there are 8 power n squares in each iteration. After the nth iteration, you will get 8 power n number of subsquares, each of its sides is 1 by 3 power n. Again we will define the measure as the combination of the probabilities. Then here this presentation I have take mq as the partition function, but we consider mq equal to zq in our definition, which I present in the previous lectures. Don't confuse with this notation. This mq stands for the partition function. So let me continue with this mq. So mq of delta is defined as mu I power q. So that means the mu I is the sum of I equal to 1 to n pi q power n. So it preserves the total mass equal to 1, because mu I power q is 1, so that the total probability will get 1, it preserves the values. Fine, mq will get this one, then take the delta equal to 3 power minus 1, then we have mq of delta is proposed the delta power tau q, then one can get the tau q here, then same method, then alpha q is minus d by dq of tau q, then alpha q one can get like this one. By applying the alpha q here, one can understand the different value of q emphasize different region of the measures. That means the large q region will the large probability, small, that means q is negative, region will the small probability, region will be the small probability. Now draw the, by applying the Legendre transform on here alpha q, one can get f of alphas like q alpha plus tau q, then tau q is this quantity, then q of alpha plus this tau q will give the f of alpha. Now we can plot alpha versus this curve, we will get the spectrum. As like in the Koch curve, if you take the all the probability equal to 1 by 8, so that the total probability we will get 1, then f of alpha will get ln 8 by ln 3, that is the support d here, that md if you are taking d equal to ln 8 by ln 3. Now, so if you are taking all the probability equal to 1 by 8, then f of alpha we are getting ln 8 by ln 3, which is not the spectrum, we will get the single point. Again the Sierpinski carpet is a monofractal in the uniform case. The Sierpinski carpet become the monofractal because we are getting the only one single alpha exponent, as alpha we are getting ln 8 by ln 3 again. So for that we will get the same f of alpha. Now it is explained here, instead of the equal probability we are taking the probability like this one, so that the sum will get 1, 0.2, 0.4, 5, 6, 7, 8, 9 and 5 and 0.5. So one can get the total probability as 1. So number of squares we can take 8 power n, in each iteration we have the 8 squares like this one, 8 cubes, then delta equal 1 by 3 power n, then first iteration, then the second iteration, after nth iteration it will come here, the color combinations given based on the probability. So we need to define the partition function that it preserves the probability, this will always equal to 1. Likewise we define the probability like here, the measure of each boxes, that means measure of each boxes we defined as like this one, so that the total probability will get 1. Then apply the scaling exponent tau q we need to find from the partition function. So mq is directional proportional to delta power tau q, one can get the tau q value, then here we will get the plus and here we will get the plus. Tau q is this one, taking the minus derivative of d by dq of tau q, one can get the alpha q, then applying alpha q will get the f of alpha. So the alpha q, observe that the alpha q is different value of p and the q, this will be the spectrum, therefore f of alpha is the multifractal spectrum. So the Holder exponent alpha q is obtained from this tau q, then by applying the Legendre transform f of alpha we can get this like this one. Now we have the probability finite sequence like this one, then for this finite sequence one can plot the alpha versus f of alpha curve, which look like this one. This is approximately given here, the values are approximately given. One can observe that if you are plotting perfect, one can get the what is the small value of alpha and maximum value of alpha, but finally the curve will get like this one, and where the small alpha the higher density will come, in the large alpha the smaller density will come, that means the points are spread out when alpha is larger alpha. If pi all are equal, then we are getting alpha equal to ln 8 by ln 3, that means the constant value, therefore will be the single point. So in that case it is an ordinary Sierpinski triangle. Yes, all the boxes, if you are giving the same probability, then we will get the ordinary Sierpinski carpet, that is called the monofractal. There is no non-uniform distributions. It is the similarity, self similarity in the same manner. Whereas when you introduce the probability, the self similarity will becomes the random scale. So, the random fractal one can get. Though after introducing the probability, if all the probabilities are equal, then we are getting the monofractal, since that alpha and f of values are equal. Now, the summary is the preceding two examples illustrate multifractal measure supported on a deterministic fractal, Koch curve and the Sierpinski triangle. So, in particular, unequal probability, it gives the multifractal measures. So, it is useful when you are taking the probabilities are unequal, then we will get in the multifractal nature. If you are taking the equal probability, that means the probabilities are uniformly distributed in the set, then we are getting the monofractal measure. That means the box counting dimension is enough, with the support we are getting as a both the Sierpinski and the Van Koch curve, we are getting the simple alpha. That means alpha is the fixed value, it is a constant, therefore f of alpha also we are getting the constant. If we are drawing, we will get the single point that equals the box counting dimension, that means the fractal dimension of an object. So, in the equal probability, one can get the monofractal for a uniform measure. Thus, the complexity of the measure arises from the non-uniform distribution, that is the heterogeneous distribution of the masses or probability, even though underlying geometry support remain deterministic. Underlying geometric support remains deterministic, because support we are taking as the fractal dimension, the procedure also we are taking with the deterministic procedures. Fine. Let me give the comparison between the fractal and the multifractal here. A fractal has the same scaling behavior at every point. It characterized by a single exponent in the monofractal case. In the multifractal case, a multifractal has a different scaling behavior at different points. It recurs a whole spectrum of exponent. The fractal object, if you are finding the single exponent that we can obtain from the multifractal side with a single exponent, it is enough. If the points are the non-uniformity, then the multifractal has a different scaling exponent at different point. It recurs the whole spectrum of exponent. Here, the scaling measure is mu of b delta of x is directional proportional delta power alpha, same alpha for all x. Here also the measure of the box we are finding, here also the measure of the box. With respect to the scaling exponent alpha, if this alpha is fixed number for all the measure of the boxes, then this is play the monofractal. If the alpha is varying with respect to the different x, then if alpha is depends on the q in our case, then it is the multifractal case. Here the scaling exponent single value, alpha is constant. Here alpha is range over from alpha min to alpha maximum. In the alpha min, it will give the high density. In the alpha maximum, it is the low density. A single point f of alpha equal to d arise at alpha equal to alpha naught, where this d is called the fractal dimension. Here a continuous curve f of alpha, in particular the concave curve, giving the fractal dimension of the subset of points which with the alpha exponent, that means the singularity exponent alpha. All parts looks statistically similar, whereas sometimes we will get the exact self similar also in the monofractal. The Cantor set also we are finding the multifractal measure that we are getting the single point. So, the statistical sense or the exact sense. Here different part have the different local dimension, self similarity or non self similar. In here, if the distributions matter, the behavior of the dimensions, the parts have the different local dimension. When you are covering by the balls, the different alpha we have, that means the different boxes have the different measures. So, here typical examples are Koch curve, Sierpinski cascade, Cantor set with equal weights, regular branching patterns. the turbulence, cloud structures, rainfall, financial time series, internet traffic, diffusion limit aggregation. These are all the example for multifractal in the real times, whereas here already applied on the Cantor bar with unequal intervals, and also the cut and paste Cantor set in dyadic Cantor set, and also dyadic Sierpinski triangle. These are all the example with we are associated with the deterministic manner also, but it is the multifractal natures. Even in the previous example, we constructed the Koch curve and the Sierpinski carpet. Both are by the deterministic manner. By introducing the probability, we can make it as the multifractal structure. Apart from that, there are real-time examples. The turbulence flow, because the distribution of here the distribution is not a uniform, it is a heterogeneous manner. So here the blue mention the low density and high density is mentioned as red line. So then the local Holder exponent is alpha x, that means alpha max with the high density, the high alpha, the smooth one is red color. Here in the iteration process of Van Koch curve, measure with equal weight, that means the probability with equal weight. Again it is the here in all the case it is the equal weight, the uniform distribution. So alpha x we are getting log 4 by log 3 in the all the things. So if you are plotting the alpha with f of alpha, we are getting the single exponent, not a spectrum. So when we get the spectrum, only when this alpha is varying from the different boxes, the alpha must be the in the interval, otherwise we will get the single points. So here in the case we will get the spectrum, many dimension fill a range over the, so alpha min to alpha max. So all point have the same scaling exponent, the spectrum collapse to a single point. This is the monofractal. The different point have the different scaling exponent, the spectrum is a curve, that means we will get like this one, the multifractal. When q equal to 0, we will get to curve, and q equal to 1 and 2, q equal to -1, q equal to -2. Then we can get the dq versus q also, and tau q versus q also. Both are decreasing curve. There is alpha versus f of alpha, we can get the spectrum like this one. From here also one can find the multifractal dimensions, that means the generalized fractal dimensions. So here the typical examples are the Sierpinski triangle, Cantor set, Mandelbrot sets. Here the equal weights, even in the unequal ratios also we will get the same thing. Only when we are introducing the density here, we will get the multifractal spectrum in the Cantor set and the Sierpinski triangle, and this boundary has a fractal dimension here. Here in the multifractal thing, there are cloud structures. These structures has the multifractal natures, and rainfall intensity has a multifractal characteristic. It is the distribution is the heterogeneous manner. The financial time series, it is has the more fluctuation, though it is a statistical self-similar, it has the more fluctuations, it has the multifractal nature. DLA, diffusion limit aggregation, follow the multifractal the natures. So here there are some examples we discussed which stands for the multifractal nature. Then we convert the multifractal to the fractal by fixing the probability in equal for the all the interval in the Van Koch curve, as well as the Sierpinski Garford for all the square. If we fix the probability as equal, then it will be converted as the fractal natures. Thank you. So the reference are given here. Thanks.